yesterday, I'll just talk about the session that we did, I did. We had two threads. Okay, the first thread, thread 1, we talked about concepts and the definitions of concepts, and we talked about evaluating concepts. So we talked about things like what is a mother, what is a grandmother, what's a child, what is circumscription, what is perpendicular, etc. That was one thread. Yeah, alpha scription. Yeah, I forgot the terminology, alpha scription and so on. This other thread, and these are closely related threads. We talked about proof. How do you establish something? Some academics use the word proof to refer only to mathematical proofs. But there is also, people also talk about experimental proofs, proof in the law court and so on. So the lawyer says, I will prove that the accused is guilty. Okay? You could, instead of talking about the word proof, you could talk about the word justification. You could talk about evidence. So I'm going to use these words in a somewhat, people use the word argument. Instead of saying, what's the proof for this? You could say, what's the argument for this? There are slight differences in meaning, but I'm going to be deliberately switching across these words. The kind of proof that we used yesterday was a mathematical proof. But there are other kinds of proofs, and one of them is scientific proof. Within scientific proof, there are different kinds of proof. But I want to give you a flavor of what that means. The mathematical proof has things like axioms, definitions, conjecture, reasoning, and then when the conjecture is proved, it is called a theorem. That is broadly the kind of terminology that you find. You'll find some of them in other places as well, but this is what we did yesterday. So for example, to prove that there cannot be a grandmother who is younger than the grandson, this is what we used. Biological grandmother and so on. Let's switch from this kind of proof to another kind of proof. Suppose you want to prove this statement as a scientist, that there are no grandmothers who never had any children. Let's say stick to this part. There are no grandmothers who never had any children. How will you do it? Well, can anybody suggest, without using mathematics, etc. Yeah?
Using biology.
Yeah, like in biology, how would you prove this? I give you a research project, okay, in the science class. So you can't use mathematical style of thinking. You have to use a scientific style of thinking. And I will give you, I told you yesterday that I'm usually generous only on Mondays. Before lunch. Occasionally,
Tuesdays.
some in random ways, sometimes I'm also generous on Tuesdays. And so, yes, of course, before lunch. So I want you to think about the notion sample and population. Are you familiar with these words?
Yes. Yeah.
Okay. So there is the population of grandmothers. Right? And you want to say something about that population. You want to make a claim about that population, namely, in this population, there will be millions of them. You can't meet all of them. In this population, there is no one who doesn't have a child. I mean, who has never had a child. Child may have died, that doesn't matter. How will you prove that?
Data collection.
You collect data, okay.
Yeah.
What does that mean? How do you collect data? You take a microscope and Go to the laboratory? No.
Survey.
Yeah.
We
Survey.
go to the people
People.
and we take average some 30 or 20 grandmothers.
Okay, so that's called a sample, right?
Yes.
You take a sample of 30 grandmothers,
And check it out if they have children or not.
yes, and find out if they have children. And suppose it turns out that among the sample of grandmothers that you have taken, everybody has had at least one child.
Yeah.
Now, is this claim proved?
Scientifically.
Is it scientifically proved?
No.
No. Why is it not proved?
We
Might be
exception
there
for
might be
somebody
somebody outside the sample who has not had a child.
Okay, so one of the characteristics of scientific claims or scientific conclusions is that it is never, unlike in mathematical inquiry, it is never completely certain. Alright? So, what you can say is that there is a strong likelihood that this is true about the population. How will you increase your confidence?
By taking more samples.
More and more sample. So the larger the sample, the larger your confidence. Okay? So instead of taking 30, if you took 300 and you found no one in that, suppose you take 1,000 and not a single childless grandmother. If you take 10 million, again same. But even if you take 10 million, there might be somebody who is there who is a childless grandmother. So this is never completely certain. So there are two ways of doing this in this kind of reasoning. You can either say there is a very high probability, 99.999% probability, in which case you are safe. But statistics in these cases will not let you say that for reasons I'm not going to go into right now, because if you don't have any variability in the sample, statistics has nothing to say. This is a weird thing, but let us keep that aside. Another way of putting it is to say, until I find evidence to the contrary, I will believe this. So I'll say, I have examined 1,000 grandmothers, everybody has a child. So until I find a childless grandmother, it is reasonable to conclude that there are no childless grandmothers. That's okay, right? But there is a clause saying, until I find evidence to the contrary. Right? So that it's a signal of uncertainty. When you take such a sample, suppose you take 10,000 grandmothers from India. Do you think that's a good idea? You're talking about the population of grandmothers and you're taking 10,000 grandmothers from India.
No. All over the world.
Why all over the world?
All the people.
But do you want to take all the grandmothers in the world? No. So, okay, what is the general principle here? So when you're arriving at a conclusion from sample and you are having a conclusion about the population, this is true about the sample. You're now going to say, therefore, it's okay to say that about the population. Now, there is a word that is used in this kind of reasoning, and that word is representative. The sample should be representative of the population.
Yeah.
So, statistical inquiry and experimental inquiry are two types of inquiry that you find in science. Scientists use statistics, scientists use experiments, scientists use instruments, scientists also use theories. And there is a certain kind of different kinds of inquiry involved in all of these. So what I'm going to do is to make you do some experiments. You're going to get threads which are marked at 1 centimeter intervals, so you can measure the distance. All right. What I want you to do is to begin at, say, 1 or 0 or something, some mark. Okay. This you will say A, and then count, let's say, 5 of them, 1, 2, 3, 4, 5, and call that B. then 1, 2, 3, 4, 5, 6, call it C. Then 1, 2, 3, 4, 5, 6, 7, call it D. And what I want you to do is to put D on top of A, right, and put a pin on top of that, and then put a pin through B and through C, such that they are tightly stretched, all of them, A, B, and B, C, and C, D. That will form a triangle, right?
Yeah.
It's not as
Use a sponge. Yeah. Tightly stretched.
Right, so these are the things that you have been using, right?
Yeah.
So this is a statement about threads and drawing pins and stretching threads and measurements and so on. This is possible, right? You can create a tightly stretched shape. And so you say, okay, if it is 5, 6, 7, you can do it. If I tell you 5, 6, and 16,
No.
you can't. Have you tried it?
Yes.
You have tried it.
Years back.
Everybody has tried it?
Yes.
Okay. Now, if you want to develop scientific inquiry, you shouldn't go by your preconceptions. You should actually go and do it. Okay, for now though, we all know it is not possible. Okay? So this is no. Okay. On what basis did you conclude here? Suppose you did it actually and you discovered that you cannot do it. What is the sample size?
2.
3. There are 3 groups.
Oh,
3 of you did it. Right? Suppose you want to increase your confidence. You should probably have 30, 40, 50, and you let's say 1,000. Alright? And you find that in every case, this is the situation. So you are quite confident that this is true. Alright? Now, then it makes you wonder, is there something about these numbers? At this point, all that you know is that if you have 5, 6, 7, it is possible. 5, 6, 16, it is not possible. One might think this is because you have a 6 here and you have a 6 there. That is why. That's a possible hypothesis. Of course, you know that's a stupid hypothesis, but you should try and do that and you might discover that if you have 5, 6, 6, it is yes, if you actually do it. So that couldn't be the reason. So you try do various things and at some point it strikes you, it is because of that. Right? So you form a hypothesis. You form a hypothesis about that. What is your hypothesis?
That if the sum of 2 sides of a triangle is greater than the third side.
Okay.
It doesn't make a
The sum of 2 sides of a thread. You're talking about threads,
Okay.
right? Tightly stretched. And you write whatever it is with pins and stuff like that. You describe the object. The object is a thread with marks and drawing pins and so on. We're not talking about triangles here. We're talking about this particular thing. And this hypothesis, to test this hypothesis, you did some experiment to get this result, right? Physically you did it with hands. This is to test this hypothesis. You'll have to do some experiments, right? So you take various kinds of sides. So you might take, let's say, 3, 16, 7, then you will find that it is impossible. If you take 15, 16, 17, you will find it is possible and so on. Let us assume that you do a large number of these experiments. And in every experiment, you find that if this is the case, that is true in actual practice. Everybody understand?
Yes.
This is the scientist's way of proving a generalization about the population of threads of a certain kind. Now you have done this as scientists, and the mathematician comes along and says, why are you doing all these experiments? You don't need to do experiments. I can prove it to you without doing experiments. What would the mathematician do? Okay? The mathematician would say, look, that thread that you have, I can model that. The thread that you have is like this, right? You have a thick thread, and you have drawing pins here, and you have these marks. The thread is thick, you can see it, but I'm going to model that as a straight line. A straight line, what is a straight line? A straight line is an entity without any thickness. Can you see such an entity? Can you see a straight line? No, because straight line has no thickness. A point has no length, no thickness, nothing. Can you see a point?
No.
You can't. Point and line in Euclidean geometry are invisible entities. You're creating this in your mind. I can model this as a triangle which has 3 straight lines, and they meet. There are 3 vertices. So you may ask me, what is a triangle? And to help you understand it, I will have to draw a picture. That's a picture. This is not a mathematical triangle because you can see it. So this is a representation. This is a representation of this abstract entity called triangle, because I'm trying to help you imagine in your mind what a triangle is. But you have to be very sure that this thing has no thickness. Actually, if you measure it, you will find that it's about 2 or 3 millimeters thickness. I can't draw a triangle with this without some thickness. Then I'm going to show that in any triangle, if the sum of 2 sides is less than the length of the remaining side, it cannot be a triangle.
Perpendicular on one side.
Draw, okay. A, B, C. Draw perpendicular to what?
Draw
From B?
perpendicular from any vertex to the opposite
Like
side.
this.
Yeah.
Alright? So call it D, and this is perpendicular. Alright, after that.
So there are two right angle triangles formed, namely triangle BDC and BDA.
2 right angle triangles?
Because it's
Because it's
perpendicular.
perpendicular.
Okay, because BD is perpendicular.
Yes.
What is a right angle triangle?
Triangle.
A triangle in which
One angle is
one angle is perpendicular. Okay, if you define it that way, I'll believe you. All right. Now, so okay, I accept that these 2 are right angle triangles. Then what?
So in triangle BDC, so consider triangle BDC.
Uh-huh.
So BC is the hypotenuse.
Okay.
So then BC.
BDC, this is the hypotenuse.
Yeah, so it's the longest side of that particular triangle.
Okay.
So BC is longer than DC, obviously.
Greater.
Great.
BC.
Wait, are you saying BC is longer than?
DC. DC.
DC is longer than?
No, BC is longer than DC.
Oh, this is longer than?
DC.
DC.
Hmm.
Why should I believe you?
Yeah.
Have you proved that a hypotenuse is longer than the other 2?
Yeah. I can.
You can? You sure? Okay.
Yeah.
All right. I know that you can, but I'm trying to illustrate a way of thinking. Okay? You don't just take these sentences for granted. You say at every step, you haven't proved it yet. All right? You might think it is obvious, but quite often it may not be obvious because I drew this in such a way that it looks longer. This looks longer than that, but that may be a mistake.
I can.
Right? Yeah, I know that you can. So you prove it. So the style that the mathematician uses is define triangle, define straight line, define these things, and you get Pythagoras theorem, you get other kinds of theorems. And from these you prove that the sum of two sides of a triangle must be greater than the sum of the other triangles, right? Okay. Then the mathematician would say, here is where you switch, you prove something in mathematics and then you go back to reality. We have said you can model this as this. That is, you can model a physical object as a mathematical object. What that means is whatever is true about the mathematical object is also true about this. Therefore, here also you will expect exactly that. Okay? You have moved from physical reality to mathematical reality, done something there, arrived at a conclusion, and then say that conclusion is also true about this. Notice what we're doing is something very similar to what we did earlier. We said what is true about the sample is true about the population. Right? Now we are saying what is true about your model is true about this. Is there a possibility of mistake there? There could be an error in your modeling. Yeah. This is where again, the moment you do science, mathematics, perfect. I mean, you have proved it, it will stay forever. But if you made an error in the modeling, of course you'll have problems. So if you take an apple and you want to know the volume of the apple, you can measure the diameter and say, I know if I model an apple as a sphere, I can calculate the volume. Apple is not a perfect sphere, you can say approximately, okay? And you try this with watermelon. And you try this with bitter gourd. And you try this with a cow. What is the volume of a cow? Let's assume that a cow is a sphere. Alright? Well, it is not something to be laughed at. As long as you specify the degree, possibility of error, you know, if you say that a cow is a sphere, you know it is not a sphere, but it works. You can say approximately this will be the volume, this is the range of error. That is important. You have to specify the range of error. Okay, what is the degree of possible indeterminacy, possible inexactness, etc. Inaccuracy, let's call it inexactness. So for example, if I measure your height and I say it is 5.3, 5 feet 3 inches. I don't know what your height is. What is your height?
It is 5'3".
Wow. Okay. Suppose I discover when you actually measure it is not 5'3", it is 5'2.9". Is that wrong? No, when you say 5'3", what you mean is plus or minus something. There is always some error in your measurement. Right? But of course, if it is 5 instead of 5'3", it happens to be 10, then of course that's an error. Right? If you measure the height of a tree, what is the degree of inexactness that you would expect? Not 0.2 millimeters. Maybe 1 or 2 feet. Maybe 5 feet. If I measure the distance from here to the sun, and I say so many kilometers, and you say, no, this is extra 0.5 kilometers. Measuring the distance to the sun. 0.5 kilometers is no big deal, but if I did that with her height, there is a slight problem. Right? Yeah. So it depends upon the situation in question. Right. Okay, that's how science works. So I showed you 2 different ways of doing this. One is take a sample of triangles and show that this is true. The other is, not sample of triangles, sample of this thread object. All right, and show that it is true about the sample, therefore conclude it is true about the population. The other is model this object, physical object, as a mathematical object. Show that it is true about the mathematical object. Now conclude that it is also true about the real life object. In both cases, there will be some possibility of error. No way of avoiding it. This technique that we use here is typically the technique of a theoretical scientist. This one. Right? The theoretical scientist would say, let us assume reality is such and such. You don't see that. I'm saying, let us imagine that. Okay, that's a crucial part. And then you show that this is true about what you have imagined, and then of course conclude back. This is true about this is a characteristic of an experimental scientist. Right? And two different styles of functioning. They're both characteristics of science.